the idea for this was to take a quick look at what is a language model. The intention here is try to show you how this is working underneath, what are the design ideas around it, and what are the core limitations we can see from understanding a little bit of about the technical side of how this works. So we'll start with and try to make an analogy for language translation, trying to go from a very simple and naive language translation problem and try to convert that to a language model. And the methodology, what I said, I'm going to start with a trivial program, and we're going to go over that and try to transform it first into a simple neural network, and then in the step by step transform it into an LLM. The idea is to create the simplest program to translate one sentence, let's say in French, to another sentence in English. And the core idea is the simplest program. We're going to use a literal translation. That means word by word translation. And how would we write that code in Python? Well, we need a dictionary first. And as a reminder, a dictionary has a key and the value is from the dictionary. So in this case, we're going to put the keys are the French words and the translated word in English is going to be the value. So we are going to split the sentence into words. We are going to call this word tokens for reasons that will become clear later, but you can think as tokens are, either could be more than one word or less than one word, but in essence, for this example, it's going to be just one word. And then we're going to translate each word one by one. Again, this is not a reasonable way to do machine translation. It's just the simplest program that you can think of. So here we tokenize the text. In order to tokenize, we just split this into words. And then the translation function is just we iterate over the tokens, and then we translate each token and we put it in the output. All right, so it works basically. We put a sentence here, given the dictionary that we created, we run that function and it translates our example sentence. So what we are going to do now is to extend it a little bit. Well, what happens if a token is not in our original dictionary? For instance, we have a similar word. And in this case, instead of table, we had tables, and there's an S here at the end. But since that word is not in the dictionary, when we run our program, we have a key error that instead of translating tokens one by one, the tokens are a query, and we try to find the closest key that matches that query. So instead of trying to find directly that key and having an error, we try to find the closest key in our dictionary that matches that query. And the query is the token from the sentence. So what could be the closest? Well, a simple way of doing to find the closest key would be to find some kind of minimum distance from the query to the key. And this minimum distance could be anything. In this case, we're using the Levenstein distance, but it could be some other kind of distance. Levenstein distance is just a distance that tells you how many characters change between two words. So it's also known as the edit distance. But in this case, the key concept is that instead of doing a hard matching in the dictionary, we find the closest match to the query, and then we use that key in the dictionary. So we avoid that error that we were having before. So we generalize the program a little bit. And in this case, we can now approximately translate some words that are not in our dictionary. So in this case, if we run this example that we had before with this word that was not in the dictionary, we have something. It's not great, but it's better than the program crashing. So, okay. The topic of this conversation was about machine learning and AI and so on. And obviously this was a Python program, so we are very far from anything related to machine learning. It was a dictionary and a series of tokens. So how do we transform this into a machine learning like algorithm. We're not going to be able to use strings anymore. So our tokens were strings, but in neural networks, we use vectors. So what is the simplest way that we can do a vector representation? We have a vocabulary. For instance, in our small example, this was our vocabulary. These are all the symbols that we use in our dictionary. In our input were the French words that we had, and this was the English dictionary. So we have two vocabularies, and the length of the vocabulary was 6 and 5 respectively. How do we transform these vocabularies into numbers? So one simple way of doing this, it's actually the simplest way you can think about it, is what is called one-hot encoding. And in one-hot encoding, you have a vector which is mostly zeros, except in one position where you set it to 1. So for instance, for this word, we're going to have all zeros except here where we have 1. And for this word, we're going to have all zeros except here where this are 1. And obviously, the ones are not in the same position. They're all in different positions. So again, for the last word, if you sort alphabetically, for the last word, we're going to have a 1 in the last position. This is one way of doing this encoding. So the vector dimension is the same as the vocabulary size. So in our example, we have 6 words in our vocabulary, so the vector dimension is 6. In a more realistic example, when you have, maybe 10,000 words in your vocabulary, then the dimension of this vector is going to be 10,000. We were able to transform words which were strings into vectors that are more suitable for machine learning. And a simple way to convert this, if you wanted to code this, would be first you need the vocabulary size, you iterate over the vocabulary, and you create a vector of zeros of that length, and you set the ith position to 1. So this is a very simple code to do a one-hot encoding. And you can see that if we convert the input vocabulary here, we will get a set of words and their respective vectors. So this is a mapping. This is printed here. And the same happens for the output vocabulary, which is the English vocabulary. So we managed to transform both the input and the output vocabularies into vectors. All right, so the next item would be that we have input and the output vocabularies as vectors. So we have basically what we used to have before with where we had a dictionary and we had the keys and the values of the dictionaries. If we put all the one-hot encoded for the input vocabulary for the keys, and we do the one-hot encoding for the values of the dictionary, and we can put them all together into a matrix like this. And we have two matrices called K and V, where we have the exact same information that we had in the dictionary before, but we have it in a form of a matrix as one-hot encoded vectors instead of strings. So if you show these matrices, this is the key matrices and this is the values matrices. And what we're saying is that if you have something like one word here, the same entry here would be the corresponding value in the dictionary. All right, so this is another way of representing same information. So there's a mapping 1 of 1 here. For each key, there's a value. And this is you can check that this corresponds, for instance, in this example, one word of the key, it corresponds to the same entry, the same position in the values is going to be the word one-hot encoded in the values. So how do we find the value for one key? And let's say that we want to find this key. We know that this is the value that we should get from the dictionary. Well, what I'm proposing is that this equation gives us that. And I'm going to show you how this works. It's actually quite simple. Let's assume that you one-hot encoded here is this one, as we had before. And we multiply by the keys matrix transpose. So in essence, what this is doing is finding which row of this is more similar to the query, because we're multiplying this, and this will only match for, in this case, it's all zeros except this position where it's 1. So this will match this row here, where this position is 1. And the rest will be all zeros. So if we do this multiplication here, if we do this first part of the multiplication here, what we are going to have is a part that is matching the key as 1, and all the other ones are going to be 0. So this q times k transpose is going to be this vector. And once we multiply this, what we are effectively doing is selecting the row that is 1. So we're going to select this row here, which is the same row number that we selected here in the K matrix. So we're mapping to here, basically. And since we know that that is the one hot encoded value of the dictionary, then what's happening is that we're retrieving the value from matrix B, which is the value that we wanted to retrieve corresponding to the dictionary word that we wanted to translate. So in this case, we completed the cycle. We go from this side of the dictionary. We go all the way here. We do a one-hot encoding in the query. We multiply it by the K transpose matrix, which gives us the position, the row position that best matches the query. Once we have that, we select the same row in the matrix V, and we retrieve that value which corresponds to the other side of the dictionary. This is kind of the basic unit for creating this kind of dictionary structure. And we just prove with an example that this works. Now, if we just run the code to take a look at this example, and again, I'm going to share the Jupyter notebook later, but you have the query, which is a one-hot encoded of this. So we print the query, we print Q times K transpose. This symbol here in PyTorch, this means matrix multiplication. The T here means transposed. So we are doing Q times K transpose times V. And you can see the values here, and you can see that, again, this is the input. This is the query. This is selecting the row in the K matrix, and this is finally the value of the one-hot encoded word in the dictionary. So we have this one-hot encoded vector, but we need to go back to a string because our translation program would be you have an input as a string, you transform it into one hot, you do this Q times K transpose times V, and now we have to decode that back into words. There are many ways to do this, but one simple one is to find the closest vector matching the output. So we write a function that is to decode, where we have our dictionary, and we basically go over all the items in the dictionary, and we multiply our vector that we want to decode by the vector coming from the one hot. When we do this multiplication, this is a dot product. So effectively, since the norm of these vectors is equals to 1, what we're effectively doing is a cosine similarity. So we are matching the vector that is closest to the vector in the one hot encoded vocabulary, and we just return the best match for that vocabulary. So just to recap, this decoding, it goes over all the vectors in the vocabulary. It finds the closest one, and then it says, okay, this is the key of that vector. So we can now rewrite the full translate function in a quote unquote matrix multiplication way. So we tokenize the sentence as before. We have our key, which is a one-hot encoding of the token. Query times k transpose times v gives us the output. We decode this output vector using the output dictionary, and we have a token. And this token is going to be what we use to create our output sentence. And we can see that this actually works. And in our toy example, it translates the same way. We mentioned that this equation works like a dictionary in Python, but with a couple more tweaks, this becomes what is known as an attention mechanism. And this attention mechanism is the core structure of a language model. So we're going to go ahead and do a few more things to this. And again, we'll keep adding more and more until we reach something that looks like a language model. One of the first things that we could do is that we had this one hot encoding assumption. But again, what happens if we have a query that does not exactly match the key? And here one naive example would be, again, trying to, if we have the word table encoded here like this, where it's all zeros except one, maybe we can think about the plural going and being encoded very similarly, but instead of one, we have 0.95 or something like that. And again, this is a contrived example, but I think you understand the core idea. So what happens then? Does our mechanism still work? Well, it turns out that it does work. We just need a minor adjustment. And one of the things that we had implicitly here was that the multiplication here, the Q times key transpose, is acting like a weight selecting the rows of B. So we are selecting the rows of matrix B. So ideally, what we would like is that the vector from this multiplication should be a vector of non-negative numbers that adds to 1. So you can think about it like a weight or a probability or something like that. But we would like these numbers to be adding to 1 and to be non-negative. So they could be 0, they could be up to 1, but they shouldn't be -7 or something like that. So there is nothing in this equation that prevents these numbers to go into negative or to be adding more than 1. So we're going to have to use a function to transform this into the appropriate weights. And this function is very well known. It's called the softmax function. And basically what it does an exponentiation. So let's assume we have the here set is a vector, which equals set 1, set 2, etc. and set n. And basically what this is a positive number. We can set beta, we can say beta equals 1. And so what it does is it transforms all these numbers into, by doing an exponentiation, it transforms all these numbers to numbers greater or equal than 0. And then by dividing by the sum of those exponentiations, it basically transforms all these numbers so that they add up to 1. So the softmax function is very known. It's very used for several different things, and we're going to find it again later on. But here's a small example where you have a vector that is 0 and 10. And if you, again, in this example, beta equals 1. And if you do the numbers here for the first and the second values of the vector, you see that the numbers are the small number, which is 0, is close to 0, and the large number, which was 10, is close to 1, and the sum of these two numbers is 1. So this function does what we need to do. So, okay, so we put this function into the right after the multiplication, and then we have this new equation. Now, there's a small numerical trick that happens that when you use this softmax function with very large vectors, it tends to saturate. So one trick that people do is that they divide by the square root of d. You can think about this as, dividing by the, the, the variance or something like that. But this is essentially a numerical stability trick to make it better. So our equation is that one now. Another improvement that we can do is that if you remember the code that we were looking at in the past, we were iterating over the queries. And here we were iterating over the query numbers, and we had a for loop here. But since this is a multiplication, what we can do is just to use a matrix multiplication. And instead of having one word at a time and analyze one word at a time, what we can do is to put them all the one hot encoded words into a matrix. And then we have a matrix of the whole sentence with one hot encoded vectors on top of each other. So our equation goes to softmax of Q times key transpose divided by square root of D, and then all that is multiplied by B. So now our code looks a little bit simpler than before because we don't need that for loop. We do convert the tokens we tokenized before, and we do convert them into one hot. We just stack them on top of each other into the matrix Q. We do the multiplication. We do the softmax here, and we multiply by B. I didn't put the square root of D here for simplification, but we'll see. We'll put it later in the code. And then we decode the whole output that we had, and we put it together in a sentence. And we can see again our toy example sentence gets properly translated. So this is what it's called an attention mechanism. This is more specifically, this is a scaled because of this, a dot product because this is a dot product, and the attention is what this is often called. So you're going to see this mechanism in several papers, but this is kind of a little bit of a simplification of what attention does. We're going to revisit attention a little bit later because it does more than that. But you probably heard about people who are in the field often heard about this very famous paper called Neuro-Machine Translation by Jointly Learning to Align and Translate. This is a high-profile Joshua Bangio's lab from the University of Montreal. It was published in the 2015s. The attention head is this. We start from this very simple attention mechanism, and you can see here that we have the matrices K, Q, K, and V, and this schematic is just the this same equation, but is in a schematic way, right? It's you have the matrix multiplication that you have here, you have the scaling here. This is an optional mask. We're not going to use it at the moment. We'll come to it later. It says optional here, so we're not going to use that. Then we have the softmax component, and then we have the matrix multiplication here. So the information is flowing from the bottom to the top, this diagram. So how can we make it a little bit more flexible? Well, we can add some weights matrices, and these are weight matrices that in the process when we're training the system, these matrices would be learned from the data. And so the other question is, how do we connect the input here? Because we have one input, but we have three matrices. Well, the way that people use this is that they have the input here, and this input flows to these three matrices and creates the Q, K, and V matrices respectively, and then it flows all the way to the output. And how do you code this attention mechanism in a few lines of Python? This attention head is quite simple actually. Here we're using PyTorch, and you always create a class that inherits from the module, and you have a forward function that has an input of has your input. You have to write that down, and obviously you write the initialization code. We are writing the query key and value matrices multiplications. So we are writing this part here, these three matrices. And how do you write that in PyTorch? Well, there's something called a linear layer. A linear layer is just a matrix multiplication times the input plus some kind of bias. But if we say that bias is false, then what's going to happen is that we're not going to add this part. So it's just a matrix multiplication. So basically, we can write off each of these matrices as what is called what PyTorch already provides us with this linear class that performs just what we want to do. So once we initialize this, how does the attention head work? Well, you multiply the weights of the key matrices. So this is WK times X. This one here is WQ times X, and this one here is WV times X. So you have the three matrices here, and then you just perform the equation, transpose Q matrix multiplication A transpose. We multiply by the shape of the K matrix. This is actually the parameter D. And since this is exponentiated to the 0.5, this is the square root of D. So we are doing the normalization. And then we perform the softmax of that. And then we do the output. And here we'll return the output of this equation. So this is just the code for an attention head. And one thing that I wanted to do before going forward with the transformer stack is to make sure that we revisit a little bit of how tokenization and encoding. So previously we tokenized by just splitting a sentence into words. Now, this is a very naive way of doing it. This is actually the code. It's kind of a half line code to split this, but we can do better. And there are many papers published on how to tokenize and so on. There's a lot of ideas in the field. One that is very popular is something called BPE, which is called, it's a byte pair encoding. BPE was originally proposed as a simple compression algorithm. And one of the advantages that it has is that it can tokenize subwords or composed words, or it can do a better job at those kind of situations. A naive example is the word breakfast. It's break plus fast, and that would be, instead of having one token for one word, it would have two tokens, and that might allow the machine translation to perform better, particularly in languages that have a lot of composed words. So byte pair encoding, in this case, the example is for data compression, but it's the same for tokenization. The idea is that you have some kind of input string here, and let's assume that this is your data, and you're trying to train the tokenizer. So you're trying to get a tokenizer from this. So first you select the most common pair of symbols. That's why it's called byte pair encoding. You select the most common pair of symbols, and you assign these symbols to a new symbol. You create a new symbol. In this case, the new symbol is called set. and you say of this, now I'm going to call it like this. So you replace that and you start again, and you find this second, the next more common symbol, and in this case is AB. And you say, okay, I'm going to replace AB with this new symbol that I created. So you replace that, and then you find again the most common symbol, the most common pair of symbols. And you say, oh, I'm going to replace this symbol with this new one that I created. And this is your compressed, let's assume that we finished the iterations here. This would be your compressed string. So you go from this to this, and obviously you have the replacement table where you can go back and forth from one or the other. So once you trained this algorithm, you have this table, and then you can tokenize, you can encode or decode using this table. The other thing that we have is the encoding that we did before. And what we used was a very naive one-hot encoding. And we can do a little bit better. We can use embeddings. And embeddings is actually a very simple concept, which we're going to touch base on now. There are many embeddings. A very famous one is Word2Vec or Glove, but there's a full field dedicated to this. There's a lot of papers around, but just to get an understanding of what this means, the idea is that we go from a token or a word into an embedding vector. And this vector is a vector of values. And in our previous case, it was one hot encoded. So there was all zeros except one, a position where this was one. In this case, the idea is instead of having, let's say you have 10,000 words in your vocabulary. So instead of having vectors that have all zeros, you have almost 10,000 zeros, and there's one position where it's one. What you could have, and this vector has length of 10,000. What you could have is an embedding, which is a smaller vector, and it has different numbers that are not restricted to 0 or 1. So you have, in essence, a richer representation because you're compressing all those into a vector of length. Let's say here, instead of 10,000, you have a vector of length, I don't know, 256, something like that. So you're trying to compress all the information of the vocabulary into this. How do you create an embedding? How do you make these vectors? How do you assign them? Well, the concept is that you start by building a data set, and then you train a model to create those vectors. So how do you create a data set? Well, you start with a sentence, let's say, and then you have a sliding window. And you're going to, in this example, there are many ways of doing this, but in this example, what we're going to do is to try to use the previous words of a sentence to predict this word here. So we're going to train a model to do a prediction given the previous words, try to predict the following. So we do a sliding window and we grab two words and we put them in the data set. So there's the input words and the output ones. And then you slide the window and you grab, another two inputs, one output. And you keep doing that until you go over the whole sentence. And but where do you get these sentences from? Well, one simple strategy would be to grab Wikipedia and to run this over the whole Wikipedia. You grab all the data in Wikipedia and you have a lot of text there, most of the text, let's say in English, and then you run this and you create a data set based on that. And once you have that, what you can do is to train the model. So the model starts with, obviously, this is a neural network model. So you start with an input, and the input is, you cannot use strings as before, but the inputs are one hot encoded words, like we did before. The output is a prediction of the next word. So this is going to be, like a softmax layer here, where you have a probability of the next word, and you train the model based on that. And the idea is that here you have n words, one hot encoded, and here you have one word which is encoded as a probability. So you run the data through, you compare the probability with the correct one hot encoded output. And the idea is to maximize, if the correct output is this, the idea is that this node should be close to 1, while the other ones should be close to 0. And then once you have the error, you propagate that by using back-propagation, which is a standard algorithm for training these networks. And once you train it over a huge data set, you grab this hidden layer and you use that as the weights, as the embeddings. So in a nutshell, what happens there is that people observed some time ago that if you project those into two-dimensionals, have several properties. The distance between woman and man seems to be similar to the distance between queen and king. So there seems to be a relationship that is somehow learned by doing this kind of training. Here they put the company CEOs for different companies group in different ways. Here another example is the group that seems to have the same structure for zip codes and cities. And here the relationships between words like strong and stronger, clear and clearer, soft and softer, than darker. The relationship seems to be similar as well. So it looks like the underlying model is learning something about the vocabulary and not just giving you random numbers. So that's all that we're trying to they are trying to show here with these structures. So in essence, what happens is that at first we started with tokenizing using words and using one hot encoding, but there are much better ways of doing this, and there's a whole lot of literature. But using embeddings is more efficient than using one hot encoding directly. Using tokenizations like BPE is a little bit more efficient. So these tricks add to the model, and then we can use these to build a better model. So I think it's probably a good time to stop. In the next one, what we're going to do is we're going to get back to our attention head that we had here, and we're going to transform this attention head into what is called a transformer. A transformer is an architecture that allows you to do machine translation as well as to build language models. So let's recap what we did so far. We started with a very naive implementation of a language translation. The idea was to do a literal translation using a simple program in Python. We created a dictionary. The dictionary, then we tokenized the words into the sentence and translated one by one using that dictionary. And then we moved that into a machine learning model, machine learning, quote unquote. We're not there yet, but we started by doing a one-hot encoding because obviously we cannot use strings in a machine learning model. So we coded them as vectors. We then created a similar structure for a dictionary, which is this equation here. We generalize it a little bit by adding the softmax. We were able to see that this also generalizes to vectors that are close but not exactly matching the ones in the keys. Then we added this multiplication as a matrix instead of iterating over the queries, and we have this attention mechanism. We also went through the how do you use this attention mechanism when you have an input and an output, and how to code it. And then we improved the tokenization, and we improved the one-hot encoding by using embeddings. And next, we're going to do a transformer block. And well, what we're going to see in the next session is what is a multi-headed attention. And there's another part of the transformer block, which is a nonlinear feed-forward layer. And then we're going to start stacking blocks on top of each other to create a stack of attention blocks. But then we're going to run into a little bit of a problem when we start stacking networks, and we're going to need a little bit of normalization, skip connections, and dropout to be able to train our model more efficiently. So, but once we add that, we pretty much have a transformer which we can use as an LLM architecture.